Download this code from codegive.com, link in the description below. Nltk Tutorial 11, Sentiment Analysis with tf-idf using Nltk and Python. This tutorial will guide you through performing sentiment analysis using the tf-idf, term frequency inverse document frequency, approach with the Natural Language Toolkit, Nltk, in Python. We'll cover 1. Introduction to sentiment analysis and tf-idf. 2. Setting up the environment and importing libraries. 3. Data preparation, loading and cleaning data. 4. Feature extraction with tf-idf. 5. Training a sentiment classifier, naive Bayes. 6. Evaluating the classifier. 7. Making predictions on new text. 8. Addressing limitations and further improvements. 1. Introduction to sentiment analysis and tf-idf. Sentiment analysis. Sentiment analysis, also known as opinion mining, is a natural language processing (NLP) technique used to determine the emotional tone behind a piece of text. It classifies text as positive, negative, or neutral. Applications are widespread, including analyzing customer reviews, social media monitoring, and understanding public opinion on various topics. tf-idf, term frequency inverse document frequency. tf-idf is a statistical measure that evaluates how relevant a word is to a document in a collection of documents, corpus. Term frequency, tf, the number of times a word appears in a document. td, equals, number of times term t appears in document d, total number of terms in document d. Inverse document frequency, IDF, measures how rare a word is across the entire corpus. It gives higher weights to words that appear in fewer documents, as these words are considered more discriminative. IDF, TD, equals log, total number of documents in corpus d / number of documents containing term t. tf-idf score *, the product of tf and idf. tf-idf, tdd, equals tf, td, *idf, td. Essentially, tf-idf helps us identify words that are important in a specific document while downplaying common words that appear frequently in many documents. In sentiment analysis, we use tf-idf to represent text as numerical feature vectors that can be fed into machine learning algorithms. Why tf-idf for sentiment analysis? tf-idf offers a relatively simple yet effective way to convert text data into numerical representations. By considering both the frequency of terms within a document and their rarity across the entire corpus, it can capture the importance of words in expressing sentiment. Words like amazing, terrible, or disappointing that are rare in general language but appear frequently in reviews with specific sentiments will have high tf-idf scores and be considered informative features for our model. 2. Setting up the environment and importing libraries. First, make sure you have Nltk and scikit-learn installed. Now, import the necessary libraries in your Python script. Explanation **** Nltk, the core library for natural language processing. **random, for shuffling data. Nltk.corpus.movie_reviews, a corpus of movie reviews with positive and negative labels. You can use other datasets if you have your own. Nltk.classify.scikit-learn allows us to wrap scikit-learn classifiers for use with Nltk's classification framework. *learn.feature_extraction.text.tf-idf vectorizer, the class for creating tf-idf feature vectors. *learn.naive_bayes.multinomial_nb, a naive Bayes classifier suitable for text classification. We'll use it as our primary sentiment classifier. *learn.linear_model, logistic regression and SGD classifier for comparison. *learn.svm.linear_svc, support vector classifier for comparison. *learn.metrics, for evaluating the performance of our classifier, accuracy, precision, recall, F1 score. *pickle, for saving our trained model to disk. *string, for punctuation removal. *stop words, for removing common words. *wordnet lematizer, for reducing words to their base form. 3. Data preparation, loading and cleaning data. We'll use the movie_reviews corpus as an example. If you have your own dataset, adapt this section to load and process it. Explanation *load_data, categories, loads movie reviews from the Nltk corpus for specified categories, POS and NEG by default. It returns a list of tuples where each tuple contains a list of words in the review and its category. *clean_text, text, this function cleans the text using several techniques. *lowercase the text. *removes punctuation marks. *removes common stop words, e.g. the, a, is. *lemmatizes words, reducing them to their base form, example running becomes run. The code then applies the clean_text function to each document in the loaded data, producing a list of cleaned documents. The data is split into training and testing sets, 80/20 split. 4. Feature extraction with tf-idf. Now we create tf-idf vectors from the clean text data. Explanation **tf-idf vectorizer, max_features equals 5000, creates a tf-idf vectorizer. *max_features equals 5000, limits the number of features, words, to the top 5000 most frequent words. This helps to reduce the dimensionality of the feature space and improve performance. You can adjust this value. *tf-idf_vectorizer.fit, train_texts, trains the vectorizer on the training data. This calculates the IDF values for each term in the corpus based on the training set. It's crucial to fit the vectorizer only on the training data to avoid data leakage. *tf-vectorizer.transform, train_texts, transforms the training text into tf-idf vectors. Each document is represented as a row vector, and each column corresponds to a term. The values in the vector are the tf-idf scores for each term in that document. *tf-vectorizer.transform, test_texts, transforms the testing text into tf-idf vectors using the same vectorizer that was fitted on the training data. This ensures that the test data is represented using the same feature space as the training data. 5. Training a sentiment classifier, naive Bayes. We'll train a multinomial naive Bayes classifier using the tf-idf features. Explanation *multinomial NB, creates a multinomial naive Bayes classifier. This is a good choice for text classification because it handles discrete features, word counts, well. *train_labels, extracts the sentiment labels, example POS, NEG, from the training data. *classifier.fit, train_features, train_labels, trains the classifier using the tf-idf feature vectors and their corresponding labels. 6. Evaluating the classifier. Evaluate the performance of the classifier on the test data. Explanation asterisk. Asterisk test underscore labels, extracts the true sentiment labels from the test data. Asterisk classifier dot predict, test underscore features, uses the trained classifier to predict sentiment labels for the test data based on the tf-idf feature vectors. Asterisk accuracy underscore score, test underscore labels, predictions, calculates the accuracy of the classifier by comparing the predicted labels to the true labels. Asterisk classification underscore report, test underscore labels, predictions, provides a more detailed evaluation, including precision, recall, F1 score, and support for each class. 7. Making predictions on new text. Now, let's use the trained classifier to predict the sentiment of new, unseen text. Explanation asterisk. Asterisk predict underscore sentiment, text, vectorizer, model. This function takes a text string as input, cleans it, transforms it into a tf-idf vector using the trained vectorizer, and then uses the trained classifier to predict its sentiment. Asterisk the code then demonstrates how to use this function to predict the sentiment of 3 example texts. Asterisk saving the model asterisk demonstrates how to save both the trained classifier and the tf-idf vectorizer to disk using pickle. This allows you to load and reuse the trained model later without having to retrain it. Asterisk loading the model asterisk shows, commented out, how to load the saved model and vectorizer from disk. 8. Addressing limitations and further improvements. This tutorial provides a basic sentiment analysis implementation. Here are some limitations and ideas for improvement. Asterisk data dependency asterisk the performance of the classifier heavily depends on the quality and representativeness of the training data. If the training data is biased or doesn't reflect the types of text you want to analyze, the results may be inaccurate. Asterisk context and nuance asterisk tf-idf doesn't capture context or nuance in language. For example, it may not be able to distinguish between sarcasm or irony. Asterisk feature engineering asterisk we used a simple tf-idf representation. Experiment with different feature engineering techniques, such as asterisk n-grams asterisk consider sequences of 2 or 3 words, bigrams, trigrams, instead of just individual words. This can capture some contextual information. Asterisk part of speech, POS, tagging asterisk include POS tags as features. For example, adjectives are often strong indicators of sentiment. Asterisk sentiment lexicons asterisk incorporate sentiment lexicons, lists of words with known sentiment scores, to augment the tf-idf features. Asterisk advanced models asterisk explore more sophisticated NLP models, such as asterisk word embeddings, word2vec, glove, fast text. These models represent words as dense vectors based on their semantic relationships. They can capture more context and nuance than tf-idf. You can use pre-trained word embeddings or train your own. Asterisk recurrent neural networks, RNNs, and transformers, BERT, Roberta. These models are designed to process sequential data like text and can learn complex patterns in language. Transformer-based models like BERT have achieved state-of-the-art results in many NLP tasks, including sentiment analysis. Using transformers usually involves fine-tuning a pre-trained model on your sentiment dataset. Asterisk handling negation asterisk pay special attention to negation. A phrase like not good has the opposite sentiment of good. Consider using techniques to detect and handle negation words. Asterisk domain adaptation asterisk if you're analyzing text from a specific domain, example financial news, medical reports, you may need to adapt your model to that domain. This could involve using a domain-specific corpus for training or fine-tuning a pre-trained model on domain-specific data. Hyperparameter tuning experiment with different hyperparameters for the tf-idf vectorizer, example ngram_range, min_df, max_df, and the classifier, example alpha for naive Bayes, C for logistic regression. Use techniques like cross-validation to find the best hyperparameters for your data. Ensemble methods combine multiple classifiers, example naive Bayes, logistic regression, SVM, using ensemble methods like voting or stacking to improve performance. Complete code example *. This comprehensive tutorial provides a solid foundation for performing sentiment analysis with tf-idf using Nltk and Python. Remember to experiment with different techniques and datasets to improve the performance of your sentiment analysis models. Good luck.